Hello, my name is Gavin Hudgens, and I'm working with Daniel Clark on the time series forecast project for US and Arizona. Earlier, Daniel submitted a video presentation of the EDA and the work done on the Johns Hopkins Research Lab COVID-19 data. This is a link to that presentation. I thought rather than rehash the presentation that Daniel did such a good job of presenting that I would just try to add to it with some slides to show some of the additional work that we've been doing with the Arizona and US COVID-19 data. And one of the things that we had a chance to do was look at an alternative source of data. And that is the data maintained by the COVID Tracking Project, which is a volunteer organization launched from the Atlantic. This is a look at the attributes or column names that are in the tables. As you can see, we have 41 attributes. It's a lot of attributes to look at and a lot that could be considered. Here are just a couple of graphs of some of the attributes from the Arizona data set. Here we see cumulative deaths and cumulative recovered numbers. Because these realizations are of cumulative data, they'll always have a positive slope unless, in a COVID extinction type scenario, there can both be flattened to zero, or of course deaths could be flattened to zero and recovery could steepen if, for instance, a treatment that isn't a vaccine is discovered. Regardless, in the real world, which attributes are used for modeling would depend on what questions are looking to be answered. For example, here we see graphs of people currently in the hospital and currently on a ventilator. These are not cumulative but daily numbers, and using these attributes for the modeling could help drive ventilator order or production decisions or hospital staffing and resource decisions. But for the purposes of this project, we're going to kind of try to look at how fast COVID is generally being spread throughout the population. And so a variable was created, the daily positive values divided by the daily test given values. And so kind of what we can see at this first point, approximately 10% of the total tests given came back positive tests. But anyway, looking at the plot, we see this wandering behavior. We see dampening autocorrelations and peaks at about 0.14 and 0.28 in the spectral density. Okay, so if we assume that the model is stationary and look at the AICs on this, we get recommendations for an ARMA 3.1 and an ARMA 1.1. And this is to show the coefficients, the fees, and the factor tables. Looking at the ASC calculations for this, we see that the ARMA 3.1 performs slightly better, and that's probably because of this little jog that it does early in the forecast. So now let's look at a non-stationary with a single 1 minus b component. Here we see that we took out with the 1 minus b, did the differencing, and we took out a lot of that wandering. Looking at the ASC on this, we get an ARMA 610, which when you look at the ASC values, at least on the last 20, it really doesn't look too good. And probably need to do a rolling window on this or figure out why we're getting this big peak down there. It looks like this model needs some work. So finally, let's treat it with the S equals 7 component. This is what we see, and getting the AIC on that, we get this factor table with a system frequency of 0.35. Looks like it might match something here in the spectral density at about 0.35. And looking at the forecast on that, get an ASZ, which is the best we've gotten so far, 0.0091. And this is a look at the future 20 forecasts ahead. So this is the summary slide that shows the 4 models. With the ASEs, the fees, the thetas, the white noise variance. Next steps, do sliding windows for the ASEs, try to improve the model, see what better fits can be had with the seasonal model, explore the multivariate VAR and neural net models, and do the same treatment on the US data. This data is good quality and it has consistent attribute names throughout not just the US but for all the states. And of course, when you have the same attributes, it has automation potential for that. So that's it. Thank you very much.